Good morning, this is Engineering Statics. We're using the fifth edition of the Hibbler text. So let's continue off where we left in chapter 5, method of sections. Let's cover a couple more problems before moving on to chapter 6. So let's begin on page 247 in your text. This is problem 5-26. And here, as with method of sections, the desire is to find the force in specific members of the truss. So for problem 526, the members in question are AF, BF, and BC. So let's draw a diagram. This is E, D, C, B, A, F. You have a 8 kilonewton force here and a 4 kilonewton force at E. This distance here is 1.5 meters. This is 2 meters. This is 2 meters as well. And we need to make our cut from AF, BF, and BC. So straight through the bottom of the truss. Now, if we consider the top half of the truss, then we do not need to worry about the support reactions at the bottom, at A and B. So then, considering that fact, let's redraw it. You have your FAF, you have your FBC, and you have your FBF. So these are the forces that we're trying to determine that are in the members after we made our cuts. So then, using our method of sections methodology, if we take the moment about point B then we know FBF and FBC, we can ignore those forces because they go through point B and therefore do not cause any rotation about point B. Okay, so this allows us to determine FAF, one unknown to solve for. So the 4 kilonewton force and the 8 kilonewton force cause clockwise rotations about point B, and FAF causes counterclockwise rotations about point B. So a perpendicular distance from FAF to B is 1.5 meters minus the 4 kilonewton force minus the 8 kilonewton force times its perpendicular distance to B is 2 meters. Solving for FAF, get 21.3 kilonewtons, and FAF is pulling away, so it's in tension, pulling away from joint F. Next, if we take the moments about point F, and one more thing to consider, this horizontal distance we said is 1.5 meters. This vertical distance from BC is 2 meters. So if you double those, that becomes 3, 4, then the hypotenuse of this must be 5. So 3, 4, 5 is our slope triangle for this BF member. So we take out some of our moments about point F, we can neglect FBF and FAF, which will allow us to calculate FBC. So we'll have FBC, which causes counterclockwise about point F, so positive, times the perpendicular distance of 1.5 meters. We can neglect the 8 kilonewton force because it acts at point F. So we take in consideration the 4 kilonewton force, which causes clockwise, so negative. Perpendicular distance to point F is 2 meters. FBC is 5.3 kilonewtons, and it's compressing at joint C, so it's in compression. Last but not least, we can use our summary of forces in the X direction to determine FBF. So that'll be 4 kilonewtons plus 8 kilonewtons minus FBF. Our X component would be, we said this was a 3, 4, 5 slope triangle. So 3/5. Which is our X component of FBF. FBF is 20 kilonewtons. And that's in compression. Let's take a look at another problem. 531. Page 247 in the text. Here, they want you to, once again, this method of sections, they want you to find the force in members FE, EB, and BC. So let's draw a diagram. It's 11 kilonewtons, 22 kilonewtons, B, C, D, E, F, A. And they want us to find the force and members FE. Oh, I left off part of the drawing. This goes here. FE, EB, and BC. So a clean cut down the middle. This is where we're going to make our cut. A is a pin. D is a roller. So D just has a Y component for a support reaction. A has an X and Y component for a support reaction. So with that being said, it will be easier to work on the right side of this diagram. So let's first do our support reactions because we have to figure out the dy component. That's a dy due to the roller. So we take some of our forces about point A, some of our moments about point A. We can ignore the X and Y components of the pin at A and then calculate our unknown support reaction at D. So the 11 kilonewton and the 22 kilonewton cause clockwise rotation about point A, so they're negative. Our dy causes a counterclockwise rotation about point A, so it would be positive. Perpendicular distances are 2 meters and 1.5 meters in the middle. So it's 1.5 meters. This is 2 meters. And this in here is 2 meters. And the height of the truss is 2 meters as well. Okay. So with that being said, we have dy times the perpendicular distance of 5.5 meters minus your 11 kilonewtons times your 2 meters minus your 22 kilonewtons times your 3.5 meters. So that equals 0. Solve for your dy. You get dy is 18 kilonewtons. So now let's redraw the truss after the cut. Now that we know our dy support reaction. This is uh, 22 kilonewtons, dy 18 kilonewtons. This distance here is 2 meters. This height is 2 meters. Okay, so now we have our FFE, which is the force and the unknown force in member FE we have to solve for. We have our FEB. And we have our FBC. Okay. So using our method of sections, if we, one more thing is to get our slope triangle of FEB. So the distance of BC was 1.5 meters and the height is 2. So you double that. The ratio is 345. The hypotenuse must be 5. 345 is the ratio here for our slope triangle. So getting to work using our method of sections, if we take the moment, some of our moments about point E, we can eliminate the forces in members FE and EB because they both go through point E, which will allow us to calculate the force in member BC. Also, the 22 kilonewton force line of action goes to point E, so we can ignore that, which then allows us to just work with the dy support reaction force of 18 kilonewtons in FBC. So that'll be 18 kilonewtons times the perpendicular distance, 2 meters, minus FBC times 2 meters. FBC is 18 kilonewtons in tension. Next, if I take some of my moments about point B, we can eliminate FEB and FBC, which will allow us to calculate FFE. So here, the 18 kilonewton force creates a positive rotation about point B, perpendicular distance being 3.5 meters. The 22 kilonewton force causes a clockwise, so negative, perpendicular distance being 1.5 meters. And then FFE times the perpendicular distance of 2 meters. FFE is 15 kilonewtons in compression. Last but not least, I got some forces in the y direction. To calculate our FEB, you have FEB times the y component, which would be the 4/5 ratio from the slope triangle, plus the 18 kilonewton support reaction force at D, minus the 22 kilonewton force. FEB is 5 kilonewtons. Okay, so let's move along to chapter 6. Here we'll be talking about center of gravity. Centroids and moment of inertia. So center of gravity is the point by which the total weight of a body passes through. And when the body has a constant density, the center of gravity coincides with the centroid of the body. And the centroid, which we've covered in previous lectures, is the geometric center of the body. And if you take a look in your appendices, specifically Appendix B, and this is page or pages 814 through 815, they give you the centroid amongst other properties of different shapes. For example, centroid of a rectangle, as we've covered previously, is in the center, middle of the rectangle. So take a look at the Appendix B. Likewise, same for a circle. So in this section of the chapter, what we'll be working with is composite bodies. What a composite body is basically consists of a series of connected, simpler shaped bodies. So for instance, if I drew a shape that looked like this, you can simplify this to be a rectangle, which will be a simple shaped body, along with a triangle. So the composite is this irregular shape, but you can break it down into a rectangle and a triangle. So if we can calculate the weight, area, say center of gravity of the simple shapes, we can determine the same things for the composite body. So some terms we need to define: X bar, Y bar, and we're in three-dimensional space, Z bar, which is a solid horizontal bar on top of these symbols. These variables represent the coordinates, X, Y, and Z axes, of the center of gravity which is G, center of gravity G, of the composite body. So then X wavy, Y wavy line, and Z wavy line, these represent the coordinates of the center of gravity of each part or the simple shape that make up the composite body. So then X bar is equal to sum, because this is if it's three parts that make up the composite body, it'd be the sum of part one, part two, part three. This is a summation symbol. So it's the sum of the coordinate of each part of the composite body times the weight of that individual part over the sum of all the weights that make up the composite body. Likewise, y bar, same. And remember, these are the coordinates, x, y, and z. And likewise for z bar. And these equations are 6-4 on page 283. Now we can, instead of using the W's for weight, we can likewise use area. Or volumes or lengths, etc. So let's take a look at the example problem to gauge our understanding where we're at. If I look at example 6.4, this is page 285 in text. They want us to locate the centroid geometric center of the plate area shown. So to give us our X and Y axes. And you can already see this is a composite body. It's an irregular shape. This is origin. So this is 2 feet. This is 3 feet. This is 2 feet, and this is 1 foot. This is 1 foot. So this is not a regular shape, but you can immediately see this can be modeled as a composite part. We can model this as a rectangle, we'll say a triangle. This would be part 1, rectangle, composite part 2. But then we would have to subtract out this part here. So another rectangle oriented vertically. So this is the 3 parts. We have a triangle, a rectangle, and a smaller rectangle, which we have to subtract out to get the initial composite body because it is a irregular shape. And the question asking us to determine the centroid of the area, which we said X bar, Y bar, Z bar can give us that using those formulas. So a good way to do these problems is to construct a table. When we say segment, we're referring to each part that makes up the composite body, which we've labeled numerically, 1, 2, and 3. So we'll do a table. We have segment, area, units of feet squared, X wavy bar. This is in 2D space, 2-dimensional space. So just have coordinates X and Y, Y, wavy bar. And then our X wavy bar times area. This is in units of feet cubed. and y wavy bar times area. This is in feet cubed as well. So we have 3 segments, we said, that will make up the composite body. So the area of segment 1, which is the triangle, is half the base times the height. So that'll be 1/2. The base is 3 feet. Well, I'm not going to save units. We already know the units. 1/2 the base times the height, which is 3 feet as well. This is 4.5. I'm not going to put units. This is equal to 4.5 feet squared. X wavy bar, as we defined earlier, are the coordinates of the center of gravity of each part, simple shape. Likewise with y wavy bar. So if the origin is here, and we know from Appendix B, where our center is, centroid geometric center for a triangle is, somewhere right here, we know there's a third towards the larger side of the triangle. So the coordinates would be 1 foot from the origin for the x direction and 1 foot from the origin in the y direction. Likewise, x wavy bar times a is 1 times 4.5 cubic feet. Y wavy bar times a is 1 times 4.5 cubic feet. Now for segment 2, area of the rectangle, which we constructed, will be 3 feet times 3 feet, 9 feet squared, 9 square feet. Now remember, this is coordinates, so this has negative or positive values in the x or y direction, depending on how you set up your axes when you're working these problems. So here, the rectangle segment 2 is on the negative x direction, but the positive y direction. So the coordinate of the centroid of the rectangle would be, using our Appendix B, which is in the center for a rectangle, will be negative 1.5 feet. The coordinate for the centroid in the y direction will be positive 1.5 feet. Therefore, my x wavy bar A is negative 13.5 cubic feet and positive 13.5 cubic feet for y wavy bar A. Last but not least, the segment 3, the rectangle, which we have to subtract out. The area would be 1 foot times 2 feet, but this is negative here because we're subtracting it out. So that's negative 2 square feet. The coordinate in the x direction of the centroid of that would be 2 plus 0.5, half of 1. Remember, these are coordinates. How much far in the x direction do I have to travel to get to the centroid of the shape? How far in the y direction do I have to travel to get to the centroid of the shape? That's the way to look at it, coordinates. So it'd be negative 2.5 feet. And for the y direction, the coordinate will be 1 foot plus 1 foot, so 2 feet. That's how far I have to travel in the y direction to get to the centroid of segment 3. Multiplication should be 5. Here would be negative 4 cubic feet. So now we have to get our totals. So the sum of A will be the sum of all these, 4.5 plus 9 minus 2. So this comes to 11.5 square feet. Then my sum of x wavy bar A is the sum of this column, be negative 4 cubic feet. And my, let me back this up because in space. Will be the sum of this column here, which we said is -4 cubic feet. And my y wavy bar A is the sum of the last column, which would be 14 cubic feet. So now, to get the centroid of the composite shape, remember our formula is and from the previous page, we determined x wavy bar A to be -4 cubic feet. The sum of the areas is 11.5 square feet. Likewise, for y, divide here. So this means that for the composite shape, this is 3 feet, this is 2 feet, the origin, and this is 1 foot, 2 feet, and 1 foot. This was the initial composite shape. Then the center of gravity, or the centroid for this irregular shape, would be -0.348 feet in the x direction and 1.22 in the y direction. So somewhere, let's say right here, that's what the centroid is, the shape. And this is how we determined it. Let's work some problems out. Take a look at problem 636. This is page 288. They want us to locate the centroid of the area shown. So let's set up our problem. So we can automatically see here that this can be modeled as a square, 6 inches, every side is 6 inch. Minus a triangle. So this would be segment 1 and segment 2. Well, if you want, you could do 3 squares plus a triangle. Just choose it, whatever is the easiest way and clearest way for you to work the problem. So let's set our table up. We have our segment, area. In this case, we're working in inches, so it'd be inches squared, x wavy bar, inch. All right. For segment 1, which is the square, 12 inches by 12 inches. This is 144 square inches. The coordinates here, remember from appendix B, is in the center. So for a square, every side is even, to get from the origin would be at the origin in this case. Likewise, for the center of gravity for the centroid for in the y direction, it's right at the origin. Therefore, this is 0, this is 0, multiplication. For segment 2, area of the triangle, remember we're subtracting it out here, be negative 1/2 the base times the height. The base is 6 inches. The height is 6 inches. The coordinate of the segment 2 in the x direction, remember it's 1/3 on the large side, so let's make this a little bit clearer to see. So it's somewhere over here, and this total length here is 6 inches. So to get to the centroid in the x direction, we have to go 1/3 of 6 to the large side. So that'd be 4 inches, but it's in the negative x direction from the origin. So it's -4. In the y direction, we have to go up with the height being 6 inches as well. It's on the larger side of the triangle, so 1/3 from the end will be 4 inches in the positive y direction. Then multiplying x wavy bar times the area, that'd be -4 times 18. You have 72 inches cubed. And then for the y wavy bar times the area, it was 4 times -18, so -72 inches cubed. Total that up, your sum of your area will be the 144 minus 18. Sum of your x wavy bar times area. And sum of your y wavy bar times area. All right, so then going to our equations for the composite. X wavy bar is 72 inches cubed. And our area is 126 inches squared. Our y wavy bar was a -70. This comes out to be. So that means then for our initial composite shape, this is our origin. The coordinates of the centroid in the x direction is, and this total distance 6 inches, each side is 6 inches, would be 0.571 in the x direction and -0.571 in the y direction. So somewhere in this quadrant. Take a look at another problem. 640, same page. Here they want you to locate the centroid coordinate, but only the y coordinate here. So I just want the y coordinate of the centroid. So they said neglect the size of the corner welds at A and B. So we just say this is the x-axis. We can approximate this as a circle, 50 millimeter diameter, a rectangle. This is 110. That's the height there. And then a smaller circle, and diameter here is 35 millimeters. So if this is our x-axis, then our y, the coordinate y bar of the composite shape here, which consists of a large circle, rectangle, and small circle, will be some distance up from the x-axis. So let's get to work, set up our table. And here, they're not asking for the x component, so we do not have to worry about that. So we have our area. This is in millimeters squared. I got your y wavy bar. This is millimeters. Now y wavy bar A, which would be millimeters cubed. And we have 3 segments. We'll call this segment 1, segment 2, and the last small circle will be segment 3. So it's 3 segments here. So for the large circle at the bottom, the area would be pi r squared. So that's pi r would be half the diameter, 25 millimeters squared. The distance from the x-axis to the centroid of C1 in segment 1 in the y direction. For a circle, the centroid is right in the center. So that would be 25, what's this unit? Millimeters, not meters, millimeters. So then our y wavy bar A would be times 25 millimeters. We'll give you millimeters cubed. Segment 2, the area is the thickness here. We got to put 15 millimeters. So the area is base times height. So it'll be 15 millimeters times 110 millimeters. We'll do the math later. The y coordinate of the center of that rectangular shape, we have to count the 50 millimeter diameter of segment 1 plus the center, which would be half of 110, which is 55 millimeters. So that'd be 50 millimeters plus 55 millimeters. That's 105 millimeters. And then y wavy bar times area would be 105 millimeters times 15 millimeters times 110 millimeters. Last but not least, the small triangle at the top, area is pi times r, which is 35 millimeters over 2, diameter divided by 2, squared. the coordinate there will be the 50 of the centroid in the y direction of that segment 3 will be the 50 millimeter diameter plus the 110 millimeter length gives you 160 plus half of the 35. So that'd be 160 millimeters plus 35 millimeters over 2 to get to the centroid of the segment 3. Therefore, a wide wavy bar A would be 160 plus 35 over 2 times pi times 35 over 2 squared. So then some of my areas, doing all this math out, you get pi times 25 millimeters squared plus 15 times 1 is 10 plus pi times 35 over 2 squared comes out to be 4,576 millimeters squared. Some of my wide wavy bar A, which would be the pi times 25 millimeters squared times 25 millimeters, plus the 105 millimeters times the 15 millimeters times the 110 millimeters, plus the 160 plus 35 over 2 times the pi times 35 over 2 squared. This comes out to be millimeters cubed. Therefore, our y bar is 393,112 millimeters cubed over 4,576 millimeters squared. It is 85.9 millimeters. So that's the coordinate of the centroid for the composite sheet. And we'll stop here today. If there's any questions, please do not hesitate to send me an email. Continue to work hard and be safe.